What is vapor pressure? Well, it's a force like any other type of pressure, but it's specifically defined as the partial pressure of a gas in equilibrium with its liquid phase. What does that mean? That means that the number of gas molecules that are being produced equals the number of gas molecules that are returning to the liquid phase. So it's dynamic. There's movement between the gas and the liquid, but there's no net gain at the equilibrium point in the number of molecules of gas or the number of molecules of liquid. So what's going on with this picture here? Well, one thing I want you to notice is that the gas molecules are creating the pressure because they're in a closed container and they're hitting off of the sides of that container. So if you're trying to think, well, what is this vapor pressure? It's the actual gas molecules putting pressure on the inside walls of the vessel. In this specific picture, we're looking at increasing temperature as we're moving from left to right. That leads us into our factors that influence vapor pressure. So when we have an increase in temperature, like we do from 1 to 2 and then 2 from 3, the molecules have more energy. I often in this chapter think of the molecules as children. So I coach soccer, little kids soccer. So if the kids are low on energy, like in picture number 1, then they tend to follow directions pretty well and they're going to stay in the area that we designate for the field. But then if for some reason we get a bunch of hyped up kids, they ate too much candy, and they have a lot of energy, then we have to be more careful. Again, these are little kids and they'll have a tendency to like run off the field. And so this is what we're seeing here. These molecules, as energy and temperature increase, they're escaping from the liquid phase, from the field boundaries. It just gets worse and worse. The more energy that we have, the more of those hyper kids are going to run off. The more of those energetic molecules are going to escape. So, exactly, to finish this statement, the molecules have more energy. More molecules escape from that liquid phase. And then at that point, like in picture number 3, we have higher vapor pressure. A second factor that we need to think about are intermolecular forces. So if a particular substance, a particular liquid, exhibits small intermolecular forces, then those molecules are held together pretty loosely. It's like if you're trying to hold hands with somebody and, I don't know, you weren't really that into it and it's just like a loose hold, right? So then it would be easier for that individual molecule to escape. And just like the escape part in the previous example, that's going to result in higher vapor pressure. The converse is also true. So if we have really large intermolecular forces, so if you have a really, really decent grip on somebody, you're holding their hand like super, super tight, right? Then they're not going to escape. You got this. Then we're going to see a smaller vapor pressure. Those liquid molecules, since they're held very tightly by those intermolecular forces, won't turn into gas and won't then create that vapor pressure. What's the big takeaway from this part? Well, we have an inverse relationship between intermolecular forces and vapor pressure. So as one goes up, the other goes down. And this is really important to remember all these different trends. So we skipped over this on purpose. It's kind of hard to analyze this until you get through the other notes. So let's go back and look at this manometer. So this is used to measure pressure. And typically you have some kind of liquid that will experience movement based on the amount of pressure in the system. And so in the past, in these devices, they would use mercury, and nowadays they use ethanol or something else. They put like some food coloring in the ethanol. So which manometer has the higher vapor pressure? Well, you'd be like, okay, the one with 1 atmosphere. If it wasn't labeled though, how would you know? And so the reasoning would be that this liquid is pushed farther, this pressure of the gas, this vapor pressure right here, is more extreme than what we see on the left. And then what does this tell you about the intermolecular forces associated with the gas in the flask? So that goes back to this statement over here. We would expect this manometer on the right to have a liquid in it with less intermolecular forces. The other thing that could be going on, even though we're kind of assuming that both of these systems are at the same temperature, but if we're asked to analyze it based on temperature, we could get away with saying, well, maybe this one has a higher temperature. This question here is based on a real-life scenario. We used to do this lab where we measured the partial pressure or vapor pressure of ethanol at different temperatures. And some of my students didn't have 125 milliliter flasks in their lab drawers. So they would go ahead and use the 250 milliliter flasks, but they'd be kind of concerned that the change in the volume of the flask would somehow impact their results. And the answer to that is no. So as in this example, it doesn't matter what size flask you use, what size closed container you use, vapor pressure remains unchanged. And the reason for this is that vapor pressure is constant at a given temperature for a given liquid. So when you move the liquid to the larger flask, it'll take a couple minutes, but the extra space will allow more gas molecules to escape. And then at that point, the pressure on the sides of the walls of the flask, once enough gas molecules escape in the larger flask, will then equal the same vapor pressure. So there's more gas in this flask, and that's how the vapor pressures remain the same. That brings up a good point when I state that there's more gas in this flask. You are going to run into issues if you run out of liquid. So there must be enough liquid in the flask. So if all of a sudden someone, I don't know, they went rogue and they decided to use a 1 liter flask and they just transferred the same amount of liquid, maybe the couple drops that they had from there, it would evaporate, trying to reestablish that equilibrium vapor pressure. But if it runs out of liquid, it can't produce any more gas molecules. And at that point, it can't reestablish that equilibrium vapor pressure. So this holds true as long as you have some residual liquid in the flask to allow for the reestablishment of that vapor pressure. So these are the types of problems that you can expect relating to this vapor pressure topic. And it's really cool because it draws upon intermolecular forces, Lewis dot structures, polarity, all those topics. So your first step is to do your electron math and draw a valid Lewis dot structure. I'm taking the liberty here just drawing carbon dioxide. I've drawn it so many times I know what it looks like. Sulfur dioxide has 18 electrons, and it actually has a bent shape to it because of that lone pair on the central atom. So be really careful when you draw these Lewis dot structures. You have to capture the correct shapes. Why you have to do that is because then we can start analyzing what types of intermolecular forces are going to be present in both molecules. For the carbon dioxide, it's linear, and we have the same atom on the left and the right, so those poles would balance each other out, right? The oxygen might pull some of that electron density away from the carbon, but then this oxygen would do the same. So we're looking at something that's nonpolar. Since it's nonpolar, we know that it can't have dipole-dipole, or it doesn't have any hydrogen, so it's not going to have hydrogen bonding intermolecular forces. The only intermolecular force that we can list for carbon dioxide is London dispersion. Sulfur dioxide is bent. Anything that's bent is automatically polar. Therefore, in terms of our intermolecular forces, we know that sulfur dioxide would have dipole-dipole intermolecular forces. And then all molecules have London dispersion intermolecular forces. Sulfur dioxide has more going on. It has stronger intermolecular forces. As a result, we know that it's going to be able to hold on to those molecules, and so then it's going to have less vapor pressure. Here they said identify the substance that's going to have the higher vapor pressure. The one with less intermolecular forces will always have the higher vapor pressure. So for our next problem here, we're asked to determine if methanol or dimethyl ether has the largest vapor pressure. And the first step, always the first step with these problems, is to draw valid Lewis dot structures and do your best to capture the shapes. So the important shape here is the fact that we have a bent molecular shape around the oxygen. And this is true for both of the molecules. If something's bent, then it's polar. And if something's polar, then we can list the fact that it has a dipole-dipole intermolecular force. You might notice that the methanol has a hydrogen that's directly attached to oxygen. Therefore, we can also list hydrogen bonding as an intermolecular force associated with the methanol. The dimethyl ether has oxygen, it has hydrogen, but they're not directly connected. So it's not going to have hydrogen bonding or exhibit hydrogen bonding. We're going to write down London dispersion for both of them. where this problem gets a little bit tricky. The dimethyl ether is a larger compound. It has an extra carbon and 2 extra hydrogens. So as a result, its London dispersion forces will be more significant than the London dispersion forces in methanol, just based off of size. However, at the end of the day, remember that London dispersion is a weak intermolecular force. Hydrogen bonding is the strongest intermolecular force exhibited by covalent compounds. So hydrogen bonding puts methanol over the top. Methanol has much stronger intermolecular forces and therefore has the lower vapor pressure of the two. We'll circle the dimethyl ether because the prompt asks us to circle the compound with the higher vapor pressure. And so since this has less intermolecular forces, the dimethyl ether will have the higher vapor pressure.